Okay, let's continue our discussion of polynomials here by talking about zeros of polynomials. The first thing I would like to do is include a little nomenclature here. A complex polynomial is a polynomial with complex coefficients. A real polynomial is a polynomial with real coefficients. A rational polynomial is a polynomial with rational coefficients. And an integer polynomial is a polynomial with integer coefficients. Okay? Alrighty. Now, if you guys remember about the numbers, every integer is a rational number. Every rational number is real number. Every real number is also a complex number with zero imaginary part. But let's take some examples here. 3x squared minus 7 halves x minus 1. That would be a rational polynomial. It would not be an integer polynomial, however, because what? Negative 7 halves is not an integer, right? Okay, it would also be what? It would also, of course, be then a real polynomial. It would also be a complex polynomial. Okay, the square root of 5x squared plus x plus 1 is a real polynomial, okay, because the coefficients square root of 5, 1, and 1 are all real numbers. The square root of 5 is what? Not rational. It's an irrational number. Therefore, this number would not be what? Rational, nor would it be an integer polynomial then. It would be what? Also a complex polynomial. We could imagine what? The square root of 5 plus 0i as being this leading coefficient there, for example. Okay. This last one, x squared plus I, x plus 1, is a complex polynomial, but it isn't real, therefore it's not rational nor an integer polynomial. Okay, so just a little nomenclature there, a little terminology, and let's go on. Let's talk about zeros of polynomials here. Before I finally do that, let's do this. Let's talk about the general way I'm going to write a general polynomial here. Remember linear polynomials? We were doing stuff like this. Y equals p of x equals mx plus b. The coefficient on x had the interpretation of being the slope of a line, and b was the y-intercept. We also had quadratic polynomials. This is very, very good for remembering the quadratic formula and such. We had p of x is ax squared plus bx plus c. Assumably a, the leading coefficient, is non-zero. Otherwise, it would just be a linear polynomial. Okay. Now, for a general polynomial, we don't even know how many terms that there's going to be involved, what the degree of the polynomial is, in other words. So we can't just go A, B, C because there's only, 26 letters in the alphabet. So instead, we use a slightly different notation here. We use a subscript notation if you want to talk about polynomials in general. So I say the coefficient on x to the n is a subscript n, or for short, a sub n. The coefficient on x to the n minus 1 power is a sub n minus 1, and so forth. The coefficient on x squared would be a sub 2. Coefficient on x would be a sub 1. And the last coefficients, that's the constant coefficient there at the end, would be a sub 0, or more likely I will say a naught. Okay? So this is setting us up here for something. We'll use this symbolism later on when we're talking about things like the fundamental theorem of algebra. Okay, let's finally get to zeros of polynomials. What does it mean to be a zero of a polynomial? Well, suppose that p of x is a polynomial. A zero of p of x is a solution to the equation p of x equals 0. That's all it means. So it's a real or complex number that may be what? Maybe rational, maybe integer, but it's a number that is a solution to this equation, p of x equals 0. So it's a value in which you plug into p of x and you get 0 as a result. Okay, so let's take just a real simple example here where I ask you to find the zeros of p of x equals negative 1/2 x plus 1 squared times x minus 3. Now, this is not written in a form like any of these above. This is written in a really convenient form where the polynomial has been entirely factored for us, okay? If it's in factored form, that makes it much easier to find the zeros, okay? In fact, we're going to see they're essentially the same problem, finding the zeros and factoring a polynomial are essentially the same problem. Anyways, how do you find the zeros of this thing? Well, what I would do is take this thing and set it to 0, right, and think about solving it. Okay, so I set this to 0. Take each factor, set it to 0, and solve. You remember the zero products property? A product of terms or factors can be 0 if and only if at least one of the factors is 0. Now, if I take -1/2 and set it to 0, I'm not going to get anything. Okay, that would be a waste of time. Here I've got what? Really two factors of x plus 1. If I take x plus 1 and set it to 0, I get what? X equals -1. Okay? Now that's actually happening twice. You know, there's actually two factors, x plus 1 there. So I've actually got -1 as a 0 of my polynomial 2 times. But I'll write that down at the end there. Let's take this other factor, x minus 3, set that to 0. That means x equals 3. So here are the zeros I'm going to create as a list here. Here are the zeros of my polynomial. Here are the zeros. -1, -1, 3. Okay? I might even put these in a little set here, so put curly brackets or braces around those. Okay? You didn't necessarily need the braces there, but I actually wrote -1 2 times. That's going to be important geometrically. This is something we're going to call it multiplicity of a 0 here in a few minutes. Okay? All right, so there's the zeros, including the multiplicity of the 0 here, which I'll define formally in a minute. Okay, the factor theorem. Okay, this is something you need to remember here. The factor theorem, the idea is really simple. Okay, let p of x be any polynomial. It could be real, complex, integer, whatever. It has degree 1 or more, okay? Degree 1 or greater. Then I claim the following. This number a is a 0 of the polynomial p of x. In other words, it satisfies this equation if and only if the polynomial, the linear monic polynomial, x minus a, is a factor of p of x. Okay? So a is a 0 of the polynomial if and only if the polynomial x minus a is a factor of p of x. Okay, let's give a quick proof of this, and the proof comes directly from the remainder theorem. Let's start out. Suppose a is a 0 of p of x. What would that mean? That means p of a is 0 by definition, right? Now, do you guys remember the factor theorem said the following? R is p of a, where r is the remainder of p of x upon division by x minus a. Okay, so this would be saying from the remainder theorem what? R is 0. Well, if the remainder is 0, that means p of x is some quotient q of x times x minus a plus a remainder 0. Well, I could just drop that remainder 0 there, right? And that would imply that what? X minus a actually divides p of x. In other words, it's a factor of p of x. Okay? So there's one direction here. Now, conversely, suppose x minus a is a factor of p of x. Okay? Well, that would mean what? P of x equals some quotient times x minus a with no remainder again. Okay? All right? But what could I do here? I could say the remainder is 0. But if the remainder is 0, remember that's the polynomial evaluated at a, once again from the remainder theorem, so that once again a is a 0 of p of x. Okay? So there you go. This comes directly from the remainder theorem. Okay? Okay, let's go on here. So there's a factor theorem, something we want to remember. Let me say in essence here, let's put this more simply. The factor theorem tells us that polynomials factor in terms of their zeros, right? In terms of their zeros. Now, I mean, the factors, if a is a 0, they're factoring like this. The factors are x minus a. Now, there's various zeros here. Okay? Now, we'll see more of that as we go through here. Let's talk about the multiplicity of a 0. This is something I mentioned just a few minutes ago here. Now, let's come back. This is the exact same polynomial I had before, The zeros were what? Negative 1 and 3. Now, if you go back and look, I had negative 1 occur how many times? Twice. So we say negative 1 has multiplicity 2 as a 0. Okay? Negative 1 occurs as a 0 with multiplicity 2. Different ways of saying this. How about 3? That only occurred one time, right? That only occurred one time. By the way, you could see that up here implicitly. That's a first power on there. Okay? So you could see in the factorization how you could actually obtain the multiplicities of the 0 by looking at the exponents here on the factors here. Okay, if a 0 has multiplicity 1, sometimes we call that a simple 0. Now we'll see geometrically here when we're graphing polynomials later on going y equals negative 1/2 x plus 1 squared times x minus 3. Geometrically, what multiplicity does to the graph. Okay, now this is formal, our formal definition. A number a, which may be real or complex or rational integer, whatever, is a 0 of multiplicity m of the polynomial p of x if what? X minus a appears as a factor of p of x exactly m times in the factorization of p of x. Okay? This would be equivalent to saying that what? X minus a to the m power appears in the factorization of p of x, and no higher power on x minus a will do. Okay? So that's multiplicity of zeros. Okay? Okay, let's take some examples here. Find the zeros, I guess this would be example 2 and 3 here. Okay. This other one, I guess I'd have example 1 twice. It's essentially the same problem. Okay, let's find the zeros of this thing. Okay. I have this mostly factored out for you. Do you guys see maybe a little bit more factorization right here? Okay. I just threw this in just so you get some factorization practice. Do you see how this factors? This is actually x minus 1 to the what? Second power here. Okay? Alrighty? What would be the power on x? It would be the first power. Okay? Now, here's what I'm going to do. When it comes to the exam, you guys will set up little tables like this. We'll have the zeros and its corresponding multiplicity. Alrighty. Okay, take each factor, set it to 0, and solve. So I'll go x plus 2, set that to 0, and I get what? Negative 2. Now, how many factors do I actually have here? There's actually 3 of them, right? If I didn't write it with exponent notation, I would have to write x plus 2 3 times. Well, this is occurring 3 different times, so that's multiplicity 3. Okay? How about this factor? That's x. Yeah, don't ignore this one. Take x, set it to 0, and quote-unquote solve. Well, taking x and setting it to 0 and solving is pretty easy. It's 0. Notice that if x is equal to 0 in this polynomial, if I let x equal 0, I'm going 0 times some other things, which is what? Still yields 0, right? Okay, what's a multiplicity? Multiplicity is 1. Okay, take this last factor, set it to 0. Looks like we get 1. How many times does that occur as a 0? Twice. So it has multiplicity 2. Again, later on, we will see the geometric effects of multiplicity on our graphs. Okay, so there's the multiplicity of each of those. What would we call this one? One of the things you would say it's a simple 0, right? If it only occurs one time, sometimes we call that a simple 0. Okay, how about find the zeros of this polynomial here? Okay, all right, we have some factorization you can do, that we need to do, right? So we're going to do this. I would probably notice this. The first thing you want to do when you're factoring is factor out the greatest common divisor, or the greatest common factor from all the terms that appear in the polynomial. It looks like I can factor out x squared here. Okay. Alrighty. Okay, this is a factorization. Can you factor that? No? Well, if you're going to solve this and set it equal to 0, okay, I'm going to imagine setting it to 0, you would first think do what? X squared equals 0. that would imply x equals 0. I'm going to put it down twice, right? Because of multiplicity 2 there, right? X occurs as a factor really twice here. Now in this thing, x squared plus x plus 1 equals 0. What are you going to do? Okay? Well, what you're going to do is go ahead and use the quadratic formula. So you need to remember that. Negative b plus or minus the square root of b squared, so that'd be 1 squared, minus 4 ac. A, b, and c are all 1, so that makes it kind of easy here. So you see it's negative 1/2 plus minus the square root of 3 over 2i. Okay? So this has how many zeros? If I go to complex numbers and allow those. It has what? 1 of each of these and what? 2 of these, a total of 4, right? So here would be my zeros if I was to make out a table like I did last time. Okay. Here's my table. It would go like this. 0. And then a multiplicity. See if I can spell that right. Okay. Let's see, I had 0 as a 0. Okay, that occurred twice, didn't it? Okay, a double 0. Then I had what? Negative 1/2 plus the square root of 3 over 2i. What's its multiplicity? 1. That only occurred one time. And its conjugate here. That also occurred just one time. All right? Alrighty, there it is, a total of what, 4 zeros. This was also of degree 4. Okay, when we talk about something called the fundamental theorem of algebra, we'll see that always holds. Okay, the sum of these multiplicities will always equal the degree of the polynomial. You have to be sometimes allowed to go into the complex numbers to do that though. Okay, all right, well this should be good for a beginning introduction to the ideas of zeros of polynomials.